Hi everyone. Apparently when I wrote down the problem in class, I mistranscribed the value of the resistor. That's because I was transcribing two different diagrams, and I was doing this diagram, but then I wrote in that value of R sub L. So instead of 400 ohms, I wrote 150 ohms, and actually in that circuit, the Zener diode does not go into breakdown. So what I'd like to do to make recompense from getting that wrong is walk you through the correct problem and then show what happens in the case of the wrong problem. So let me start by just talking about the situation in conceptual terms. The Zener diode is going to have the current going in reverse bias directions. So I Zener is going to go down that way, such that the total current going through the circuit is going to be equal to I Zener plus I sub L. Now, you will notice that the Zener diode is therefore diverting some of the current that would go through this resistor, meaning that the voltage drop across this resistor is lower than it would be without the Zener diode. This is a key point. The Zener diode's voltage of 12 volts is smaller than what V sub L would be if the diode was not there. The Zener diode is actually going to pin V sub L at a lower value. If V sub L without the Zener diode is lower than V sub Z, then the Zener diode is actually going to do nothing. It's not going to be in breakdown mode. And the way that I wrote down the problem in class, that was the case. The Zener diode would have done nothing. Let's do it for the correct problem where this is 400 ohms and not 150 ohms. Without the Zener diode, V sub L would be 400 over 400 plus 120 times 18. It'd be 13.8 volts. So without that Zener diode, this is going to be at 13.8 volts. But if we have this 12-volt Zener diode here, the 12-volt Zener diode is actually going to go into breakdown mode since this voltage is higher than the Zener value, and current is going to flow through here, and this is going to pin the voltage at 12 volts. So this is going to be held at 12 volts. That means that the current going through here is going to be 12 volts divided by 400 ohms, which is 0.03 amps. Similarly, we can do the math that if this is 12 volts and this is 18 volts, 18 minus 12 divided by 120, which is the resistance of this resistor, that tells us the current through this path, and we get 0.05 amps. Now we can see that unlike when we were trying to do the problem in class, the current going through here is larger than the current going through here, and the overflow is going to be going through the Zener, such that I sub 1, the current going through here, is equal to IL plus IZ, so 0.05 equals 0.03 plus IZ, and that means that IZ is 0.02 amps. Now, let's talk about what this means. If this load were variable, so it could fluctuate in its resistance, if it fluctuates downwards, then I sub Z will draw less current because more current will go through this path in order to maintain that 12 volts. If it gets higher, then more current will go through here in order to maintain that 12 volts. So if this gets higher, it can go arbitrarily higher, and the Zener diode can just draw more and more current to maintain the appropriate voltage. However, if this gets too small, then the current going through here will be such that the Zener diode can contribute nothing to balance out the incoming current. And that was exactly what happened in the problem as I incorrectly transcribed it in class. So this was the problem as I incorrectly transcribed it in class, where this was an 150 ohm resistor. This should read ohms, and this is ohms. So in this problem, if we want to calculate what would the voltage at this point be without the Zener diode, well, it's 18 times 150 over 120 plus 150, which gives us 10 volts. So without the Zener, this would be at 10 volts. Now, if the Zener is supposed to bring us down to 12 volts, if it's supposed to take current away from this path in order to bring the voltage down to 12 volts, and we're already at 10 volts, that means the Zener diode is going to do nothing. The Zener diode is not in breakdown mode in this case, and therefore it's as if it wasn't there. The circuit is just going to be such that this point is going to be at 10 volts, and all the current is going to flow around and do nothing with the Zener diode. So those are the two extreme cases. So when you're doing a Zener diode problem like this, what you want to first ask yourself is, are we in the breakdown regime for the Zener diode? And for that to be the case, the parallel path needs to have a higher voltage without the Zener diode than with it, and the Zener diode is going to pin the voltage down.